So say you're a particularly pedantic person walking through the park when you come across an infinite line of dominoes. Yes, an infinite line of perfectly set up, equally spaced dominoes just teetering on Destiny's doormat. Was it the work of Satan or Santa? Who knows? We know you've prayed to both, you dyslexic heathen. But more importantly, who cares? Your childhood dream has finally come true. But wait, you pull back at the very last moment, remembering that you are in fact a particularly pedantic person, and should first self-reflect on why you want to knock these faux ivory suckers down in the first place. Well, after fun and national defense, you get to the real reason you want to knock them down. You want to see what'll happen. I mean, how many will fall? Probably all of them, but who knows? It's an infinite line of dominoes. This is kind of new territory. So like any kid that's ever thought they can run through walls, there's only one way to find out. You have to run the experiment. Now, fully rationalized, you excitedly go to knock the first domino down. But wait, hold up. I mean, this is an infinite line of dominoes after all. Maybe if you knock the first one down, it'll cause an infinite chain reaction that goes well out of your field of view or takes infinitely long. And who has that kind of time? Defeated, you realize there's no way to physically verify every one of the infinite dominoes will actually fall down. What if you could answer your question without ever touching a single domino? What if you could prove it would happen mathematically? So you get to writing. First with this setup. Assume the first domino is knocked over. Then by definition, the first domino will fall over. Not very exciting yet, but it's a start. We've proven one will fall. But then, since the dominoes are perfectly set up and equally spaced, the second domino is within a domino's length of the first. So when the first falls down, it'll knock the second domino over, meaning the second domino will fall down. And then the third is within a domino's length of the second. So when the second falls over, it'll knock the third down. And you follow this Mexican train dominoes of thought where it goes. Able to write a proof that the fourth domino will fall, the fifth, the 100th, the 1,000,000th, the 4,937,000th, the billionth, the 10 billionth, writing, using every single piece of paper you can find, every chalkboard, every road sign, every driveway, every Etch-a-Sketch, every one of Matt Damon's mirrors, every clay tablet, until you use every single writing surface on the face of the earth, including the face of the earth itself. Wait, that was your face. Until you've written on every single analog or digital writing surface in the world. No human being will ever write down anything ever again. The last thing ever being written. The 1,618,033,988,748th domino will fall, hitting the 1,618,033,988,749th domino. Of the infinite dominoes you wanted to prove would fall, you only proved less than 2 trillion would. Still infinitely many short of your goal. There's got to be a better way. And there is. It's called mathematical induction. So what is this mathematical induction? Well, first of all, take all questions at the end, thank you. But second off, fantastic question. To get there, though, we're going to have to talk about what it means to prove things, like anything. How do we prove anything is true? To prove something true about finitely many things is easy. All you have to do is verify the claim is true for each one of your finitely many things. So, for example, to prove that my eyes are truly a lip, bite, and green-brown, all you have to do is verify the claim is true for each of my eyes. Since I only have 2 eyes, it's really easy to check both, and since both are truly green-brown, the claim is true. So this verifying method works great for finitely many things, but infinitely many things is a different animal, unlike this apathetic goat, which is an indifferent animal. The problem is, when trying to verify something's true with infinitely many things, it's exactly like trying to show all of the infinite dominoes will fall by actually knocking them down and running the experiment. It would take infinitely long to actually go back through and verify the claim is true for each one of them. So you have to get more clever. And the more clever way to prove a claim about infinitely many things is to not look at each of your infinitely many things individually, but instead find some properties they all share. Because then, if you can prove that anything with those shared properties must logically also satisfy the claim, you've just proven the claim true about everything in your infinite set in one swoop. So say, for example, you're trying to prove that every single Disney princess is warm-blooded. Why? Why invent spam? Why go to the moon so the Russians don't do it first? And for Disney princesses, we can start here. So there's actually a lot of qualifications a girl's got to meet to be an official Disney princess. If you look at the list, by definition, for one, they have to be human. Sorry, Nala, this is the princess lunch table. The point is, every Disney princess has the property that they are human. Or put another way, if X is a Disney princess, then X must be human. Note this arrow here indicates that the top statement is logically linked to the bottom statement, meaning if the top statement is true, the bottom statement must logically follow. Anyway, we can keep going just like this. If X is a human, then X must be a mammal, because humans are mammals by definition. Also by definition, mammals are warm-blooded vertebrates. They're sometimes furry and mainly give live birth, all except for the platypus, the echidna, and possibly Ariel. She's really the sometimes Y of that group. The point is, if X is a mammal, X must be warm-blooded. Now in just these three steps, we've already formed a logical chain made of these logical links, which shows that if the top statement is true, the bottom statement must logically follow. If X is a Disney princess, X must be warm-blooded. So in particular, Belle is a Disney princess, so Belle must be human, meaning Belle's gotta be a mammal, so she must be warm-blooded. Hey, the claim is true for Belle. And we can use that exact same logic on Mulan and Merida. But wait, we're verifying again. Oh gosh, I promised myself I would stop. See, the problem is we're not taking full advantage of our logic chain here. The only reason we introduced X at all is as a placeholder for any Disney princess. And since we've already proven that any Disney princess will be warm-blooded, that means that every Disney princess must be warm-blooded for free. No ifs, ands, or buts about it. Okay, actually, we said if, and but a lot, but there's no verifying about it. That's the point. Now, time out, though. As I promised you I'd prove something true about an infinite set of things. And as we all know, there's only 12 official Disney princesses. I don't need that lecture again, Dad. But the important thing is, though, it doesn't matter how many princesses there are. Our proof never actually mentions any individual princess. So it would work just the same and be just as compact if there are 1,200 princesses, 12 million princesses, or even infinitely many. The problem is, infinity doesn't really show up at all in our actual physical world. So if we want to do an example with an infinite set, we're going to have to enter the world of math. Now let's prove something mathy sounding. Like, for example, that every even number squared is even. Aha! Now see, there are infinitely many even numbers, so this truly is a claim about an infinite set of things. And just like the infinitely many dominoes, verifying is a non-starter. I mean, we could verify that 2 is even, and 2 squared which equals 4 is even. And also that 4 is even, and 4 squared which equals 16 is even, 6 is even, 6 squared equals 36 is even, on and on and on and on like that. But that already sounds like a lot of writing. I'm getting carpal tunnel vision just thinking about it. So instead, let's make a general argument, showing that any number that has the property of being even also has the property that its square is even. Alright, so let's go ahead and let n be any even number. By definition, if n is even, then it can be divided evenly into 2 equal parts. Let's call the size of each of those parts k. So if n is even, then n equals k plus k for some whole number k. But now let's look at the square of n. Notice we can split the square in the same place as we did n. To find the square can also be divided into 2 equal parts, each of size n times k. The important thing is, n squared equals n times k plus n times k, meaning we've successfully split n squared evenly into 2 whole number parts. So n squared is also even. And just like that, we're totally done. Don't you see, we could apply this logic to any specific n. For example, to prove that 6 squared is in fact even. But we don't have to. We've already shown that any even number squared must be even, meaning that every even number squared must be even. A proof about an infinite set of things using just a handful of lines. But hey, speaking of lines, remember the dominoes? Because we now have everything we need to actually prove that every single domino will fall using just one sheet of paper. I mean, not this sheet of paper, this is the script, he says while holding the script. But with a new sheet of paper, we can totally easily prove that every single one of our infinite dominoes will fall using this generalization method, but with a twist. So let's start with what we know. We know that all the dominoes are perfectly lined up, equally spaced, each within the domino's length of each other. We've already heavily used this fact. This is how we showed that if the first domino falls, it'll hit the second, because the second's within a domino's length of the first. If the second falls, it'll make the third fall, the third will make the fourth fall, etc., etc. We did this about 1.6 trillion times or so. But the big problem was we were trying to show that each of these dominoes will fall individually. And considering there's infinitely many of them, this isn't a very scalable solution. Instead, we should look at general properties that all of our dominoes share. In particular, notice that if the nth domino falls, since it's within a domino's length of the next one, the n plus 1th domino will fall. Guaranteed, or your money back. And since this works for any n starting at 1, this works for every nth domino starting at the first one. So instantaneously, we've just proven that all of these logical links right here work. But importantly, we still haven't shown that any domino will fall other than the first one. We've just shown that if a domino falls, the next one will certainly also fall. This is where the twist comes in. See, these logical links actually all feed into each other. And applying the general argument to each one of our dominoes, we've accidentally ended up making this infinite logical chain, connecting the falling of the first domino to the falling of every other domino. So just looking at it, if we take any random number, say the number of words in the Declaration of Independence, we'll find this unbroken chain of logical links from the first domino falling leading to the 1458th domino falling. And 1458 is just an example. We've already proven that the falling of the first domino is connected to the falling of any other domino, meaning the falling of the first domino is connected to the falling of every other domino. If the first domino falls, every other domino will also fall. Proof done. And using this infinite logical chain is exactly what we call a proof by mathematical induction. And all induction proofs go exactly like this. You start by proving a base case, which is just saying that your very first statement in the chain is true. Then you need to prove the inductive step, which is just that general logical link that says if the nth statement is true, the n plus 1 statement will follow. But then you're done. Once you have that the first statement is true, and you have all the logical links here, this will start a domino effect that proves your claim is true for everything in your infinite set. As easy as 1, 2, 3. But trust me, this mathematical induction goes way, way deeper than even dominoes. It's an incredibly powerful and general method to prove claims about infinite sets, especially those infinite sets that build off each other. For example, we can use mathematical induction to easily prove a short little ditty. You might have heard of it. It's called Eulers Formula. No, not that one. Nope. Do I have to edit? Oh, yes, there it is, finally, Eulers Formula. Eulers Formula, or Euler's characteristic formula, is a bizarrely simple yet deep invariant that says for any convex polyhedra, aka a 3D undented shape, its number of vertices minus its number of edges plus its number of faces always equals 2. Always. For all of the infinitely many convex polyhedra you could imagine. So for example, a cube has 8 vertices, 12 edges, and 6 faces. And 8 minus 12 plus 6 does in fact equal 2. An icosahedra, on the other hand, has 12 vertices, 30 edges, and 20 faces. And 12 minus 30 plus 20 again equals 2. But look at me verifying again. What's wrong with me? If you know, leave it in the comments below. See, Euler's characteristic formula is very easy to state and to check. But how would you possibly prove it true for all the infinitely many convex polyhedra? Well, to start, we know that we can smush any convex polyhedra into the plane to get what's known as a planar graph, which are just networks with no crossing edges. And it turns out Euler's formula actually applies to all planar graphs. If you look at any one of these crazy looking weird planar graphs here, you'll always find that the number of vertices minus the number of edges plus the number of faces equals 2. That is weird. All of these graphs are insanely weird, unique, and different things, but they all have this one thing in common. V minus E plus F equals 2. And here's the thing to notice about planar graphs. They can all be built from each other by adding edges one at a time to the OG planar graph, the barbell. So for example, this planar graph can be built by adding edges to the barbell here, 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 and here. While the planar graph for the cube can be built by adding edges to the barbell here, 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 and here. This is exactly where induction comes in. We have an infinite set of planar graphs, sure, but they can all be built from each other. So if we can show Euler's formula holding for one-edge graphs implies it holds for two-edge graphs, and it holding for two-edge graphs implies it holds for three-edge graphs, and Euler's formula holding for 3 implies it holds for 4, on and on like that, we have a domino effect that will show that Euler's formula, V minus E plus F equals 2, holds for all possible planar graphs. So let's get to work. Remember, to start an inductive proof, we first show that the base case holds. Here what that means is we need to show that every one-edge planar graph follows Euler's formula. And there's only one one-edge planar graph, the barbell, which has 2 vertices, 1 edge, and 1 face. We always include the outside bit as a face. And 2 minus 1 plus 1 does in fact equal 2. So Euler's formula holds for all one-edge planar graphs. Now we need to do the inductive step. This is where you prove that all of those logical links work. The one saying that if Euler's formula holds for all one-edge graphs, it holds for all two-edge graphs, holding for all two-edge graphs means it holds for all 3, 3 for 4, etc., like that. Specifically, we need to show that if Euler's formula holds for all n-edge planar graphs, then it will also hold for all n plus 1 edge planar graphs. So let's consider any old n-edge planar graph and assume that Euler's formula holds, meaning that V minus E plus F does in fact equal 2. Now let's think about any possible n plus 1 edge planar graph we can build from this planar graph. Notice, if you build an n plus 1 edge planar graph from this original graph by adding an edge between any two existing vertices, sure, your number of edges will go up by 1, but you'll also split an existing face into 2. Where there was 1 face, there's now 2, meaning your number of faces also goes up by 1. So in the formula, this extra edge and extra face cancel each other out. So this new graph still has the property that v minus e plus f equals 2, aka Euler's formula still holds. But there's another way we can add an edge to this original n-edge graph. We could add an edge that doesn't connect back. In this case, our number of edges would go up by 1, sure, obviously. But also we have to add this extra stray vertex here at the end of the new edge. So our number of vertices goes up by 1 as well. So in the formula, our extra vertex and our extra edge will cancel each other out, meaning our new graph still has the property that v minus e plus f equals 2, aka Euler's formula still holds. So any n plus 1 edge graph built from any n-edge graph following Euler's formula will also follow Euler's formula. Or put a different way, if every n-edge graph follows Euler's formula, then every n plus 1 edge graph will also follow Euler's formula. And that's it! We're done! The base case here shows that Euler's formula holds for all 1-edge planar graphs, and the inductive step fills in all these logical links here. Therefore, every single possible planar graph, no matter how many edges, will follow Euler's formula. And then, since convex polyhedra are just unsmushed planar graphs, every single possible convex polyhedra across all possible edges, all political affiliations, all preferred creeds, all have the property that v minus e plus f equals 2. It's important to recognize here, folks, that this was not easy. We just proved something about all possible planar graphs, all possible convex polyhedra. Have you seen these things? They're all weird and unique and totally different. They're just networks without edges crossing. Why do they even have this one property in common? I don't know, but they do. And the only reason we're able to prove it is because of this idea of mathematical induction. I mean, there's other proofs that are harder, but the easy way is mathematical induction. That is the power of dominoes. And that power belongs to all of us. Even you, Nala. Okay, and that's our video, everybody. We are done here. Please don't forget to comment if you like this video, you want to see more. Tell us what you like. Tell us what you want to see. Comment what's wrong with me. Comment if Nala's being snubbed. Where's Tinkerbell? These are all interesting conversations to have. If you like the video, like it. Subscribe regardless. Have a great day.